Good morning, everyone, and welcome to the Go Fly Master Lecture this morning. To kick us off, I'd like to introduce Gwen Leiter, CEO and founder of Go Fly Pod. Gwen?
Thanks, Paul, and hello, good day to everybody, or good evening to everybody. We're all around the world. Greetings from JFK Airport in New York, where I am right now, about to board a flight. And we are so very excited to today bring you today's master lecture with Dan Newman. As you all know, we are sponsored as our grand sponsor by Boeing, and we are also supported by over 21 different international aerospace and STEM organizations. And today we have the great privilege of hearing from Dan Newman, who is a senior technical fellow in configuration development at Boeing. He is the chief engineer of Phantom Works, the Rotary-wing aircraft defense, space and security division at Boeing. And Dan serves as I said, the chief engineer for vertical lift aircraft research and development and supports commercial airplane product development. He previously served as a program manager at DARPA and as the technical director of AHS International Vertical Flight Technical Society, and as well as an adjunct professor in mechanical engineering at the University of Pennsylvania. He received his Master in Aerospace Engineering from the Rotorcraft Center of Excellence at the University of Maryland and his Bachelor of Science in Mechanical Engineering from Cornell University. He is a wonderful asset for us all to hear from and an all-around just amazing person. So I am so pleased today to be able to welcome Dan Newman to join us, and we all look forward to learning from you, Dan. Thank you.
Thank you, Gwen. Thank you very much. Paul, are you going to first share any other charts?
Nope, off to you to share.
Okay, I'm up. Good morning. There we go. Stand by as I wrestle with technology. Good morning. I'm going to spend hopefully 40 minutes or so sharing a whole lot of topics. Give a little bit of an overview. As I like to say, I talk at 250 knots and gust to 350. So I'll do my best to stay on topic and speak clearly, but please, I ask for clarification at the end if you have any questions. So Gwen, it was a very, very generous introduction. I'm going to spend some time today talking about what I consider an amazing discipline and an opportunity. And as you can see here, aircraft configuration, the title, it's more than the sum of the parts. It's far more than the sum of the parts. And the configurator has a unique role as an integrator. Often the blame when something happens and quiet knowledge without credit when it goes well. The team succeeds, but it's the role of the integrator, and it's often the most challenging and I think the most fun. So some topics today. I'm going to talk about form and fit, reminding you have to focus on the question, a bit about dominant configurations, and then a series of topics about perspectives of the configurator. And I'll go through these as we see, but I think these will be interesting. Let's get started. So lots of equations. Just want to clarify, that's not what this is. Configuration is an integration job, and the role is to ensure that every subject matter expert who's telling you must listen to everything they say or you won't succeed is coming at you, and they're all conflicting. And so the job of the configurator is generally not about doing the details, but it's about understanding the sensitivities and the choices and weaving a compromise to which everyone can sign on. So I cleave the world, an oversimplification as a conceptual designer, into form, fit, and function. And form and fit is design. And design is, what do the parts look like and how do they fit together? Clearances, overlap, interference, fit. It includes materials, it includes geometry and tolerances. And then function, which is, how does it perform? Does it do the job? And in the end, the question is, does it comply with the requirements? And every engineering challenge is this balance to define to assess, and then if not compliant for whatever reason, to iterate. And I tend to consider myself more in the design world, but the configuration job is primarily form and fit. But fundamentally, you're not done until the analysis has been done, and it's a balance of understanding all the requirements and the means to assessing the design against each of those requirements in order to decide whether you're done. So this is the vision. This is what people envision. It's drawing aircraft on napkins. It's doodling. I've been fortunate that I have the opportunity to do this for a living. Early in my career, I did drafting boards and sketching. Later, it's sketching and CAD. And now I have the opportunity to work with teams of people and integrate their work. But fundamentally, what we're doing is creating. And I'll just make a comment that computers are very precise and they make it rather hard to be as creative. So sketching remains a valuable talent, and then getting the computer to represent those is part of the challenge. But the creativity is sometimes in conflict with the rigor of a computer. So just a quick cartoon. What are we trying to achieve here? And knowing you're done means you need to know the question, what does success mean? So just a cartoon to illustrate, these are different means of cost versus distance of transportation, the van pool, a bus, a commercial airplane, and the cost grows with distance, but when you share that cost with others, it's lower. Or you could do it on your own. You can have private transportation and the costs are higher. Private jet's much more expensive than commercial travel. Now, what are we trying to do here with GoFly? Where, and the Uber Elevate is trying to look at joining together people and moving them around in an efficient way over short ranges, a lot of electric aircraft. But GoFly is in here at the low end. We're concerned about speed and we're concerned about range, but fundamentally, it's about the experience. It's about flying, not being flown, not as much about transportation as it is about the experience. And so here's just my little cartoon. This is what we're trying to achieve. We're trying to, some say, wear this system as opposed to ride in this system. So we want to keep the vision in mind, because the vision is what impacts decisions, especially when those decisions could go either way. The vision of what you're trying to achieve will help you make those decisions. And this is my cartoon of what you're trying to do, the rules, and a cartoon of the fly-off. And again, keep in mind the objective. Every decision gets you closer to that objective, and every decision is influenced by how best to get there on time and on schedule and perform as required. Just a brief tangent on what is meant by the dominant configuration. So in the beginning, there was the penny farthing, or the bone shaker, called a velocipede. And over time, they moved toward what's called the safety bicycle, but we just call it the bicycle. It's the dominant configuration, but it's not the only one. There are exceptions. We still, in some ways, refer to them as bicycles, but they're not exactly the two-wheel dominant configuration. And the same is true in aircraft. We started out with the first successful manned-powered aircraft, 1903, and then we moved on. Boeing, the Boeing in Westervelt in 1916, the beginning of our company with a biplane. But what's really interesting is a statement in Scientific American at the time, where they were so sure that that was the best that you could get to, the dominant configuration. There was a statement that they would entirely fill the sky with biplanes and move away from monoplanes, which of course we know isn't true. And now when people say a commercial airplane, this is the commercial airplane. This is what they think of. Twin engine, swept, high subsonic, pressurized commercial airplanes. But there are exceptions. There's turboprops, there's 4-engine aircraft. Exceptions, the dominant configuration is the twin engine aircraft, but there are exceptions. So again, there's a dominant configuration and there are exceptions for specific reasons. And this is a chart from DARPA, Paul Eremenko of DARPA, called The Tyranny of the Dominant Design. And you can see over time across the bottom and metrics going up, and these curves tend to converge and they level off because those dominant designs are getting optimized. And we're fixing the parts, we're fixing the system, and then we're optimizing the parts better engines, better materials, better aerodynamics. And over time, that dominant configuration improves, but it levels out. So it gets harder and harder to justify replacing it because you can't find this kind of significant improvements that come early in some field, some domain. Now we go to vertical flight. Early on, the lateral twin aircraft, you'll notice this is aircraft versus airplane, because we're not talking about conventional takeoff and landing. And it's a little bit of a busy chart, but over time, helicopter configurations, and again, the dominant configuration is two rotors, single rotor with a tail rotor, the tandem, the lateral twin, the tilt rotor. Only on the upper right do we have a single rotor helicopter that truly only has one rotor, and that's because there was no need for anti-torque with tip drive. But again, there's a whole series of configurations here in terms of vertical lift aircraft, all with different strengths and weaknesses. But in the end, when people say helicopter, this is what they think of. It's the dominant configuration. And as I said, there are exceptions. They also qualify as helicopters, but they're not what people think of. So that's the meaning of the term dominant configuration. And again, the metrics tend to level off until you make a dramatic change to the configuration. You get what you get. And you need to really come up with a technology breakthrough, perhaps at the subsystem level, if you're really going to see improvements. But nowadays, there's no pictures here, but this is just an article, an indication. There is a huge revolution going on in terms of vertical flight, runway independent aircraft. It's spurred by the revolution in electrics, electronics, microprocessors, actuation, electric actuators, and autonomy. And people believe that additive manufacturing and materials will lead us to a new set of configurations, and eventually one may emerge because we have a new objective here. We have this small, quiet, urban transportation activity going on, sponsored primarily originally by NASA and Mark Moore, and now Mark Moore at Uber, and the Uber Elevate activity in an extraordinary number of companies. And I haven't shown any pictures here, but there's easily 65 designs currently in the news, and new ones every day with organizations popping up. So again, there's a new mission, but to remind you the difference between what they're trying to do with urban air transportation, urban air taxis, on-demand mobility, they're concerned with getting people from A to B, more about riders than about the experience of flying. So when you make decisions, keep in mind the difference in what we're trying to achieve with GoFly, what we're seeking you to achieve with GoFly. An old ancient cartoon, just to illustrate when you start to talk about more than just vertical lift, but going some distance, especially going a distance with some speed. There's a whole series of ways to skin this cat. Tilting the aircraft, tilting the thrusting system, deflecting the thrust, or having dual propulsion. And many of these have been tried. And there's not a whole lot new under the sun when you think about it. If you look at the left side, this was in 1959. Look at that, 6 propellers on a wing with tilting. Looks a lot like some of the electric on-demand mobility designs that are coming out. And at the top, Curtiss Wright, very successful with a tilting quad prop, and then some more designs, and there's a tilt wing on the right with 4 props in line. Many things tried, many things, they were tried military, a little bit of civilian work going on, but they're challenging because they run into the challenges of meeting all of the requirements. Many of you may be familiar, this is the original version of the Vstall Wheel by McDonnell Douglas Aircraft Corporation. And it tried to illustrate the many different ways of achieving what's called Vstall flight, vertical and short takeoff and landing. Now this included concepts that never flew. This was theory and cartoons, and it's been iterated many times. I have a collection of the iterations of it. And this is the latest, and Mike Hirschberg of the AHS has been the fundamental archivist who has done the latest version. And it illustrates the Vstall concepts. Almost every single one of these have flown. Unfortunately, it's called the Vstall Wheel of Misfortune because very few of them have actually gotten to fielding. But I don't think it's misfortune. Many and most aircraft crash in flight test and have incidents and mishaps. That's part of the game. And good judgment comes from experience, and experience comes from bad judgment. So it pains me a little bit when this is called the Vstall Wheel of Misfortune, because it really is a great testament to the amount of engineering that was done to solve some very, very hard problems. Many of these flew, but they didn't have enough payload or useful load to become a valuable product, but they still flew and illustrated. Now, only 4 of these aircraft, different types, have gotten to any kind of military fielding, and there's one on its way to civil fielding, and that's the the Leonardo AW609. And although they just pushed certification back, it's still well on its way to providing civil capability. So it's an interesting history of many different configurations, and I invite people to take a look at the Vstall wheel, just to look into all the different ways that people have tried to solve this problem. But what you should understand is that perhaps the most significant the second is probably useful load capability because of the costs associated with this challenge. But the most significant reason these aircraft didn't succeed is that they may have flown well as an airplane in cruise, and they may have hovered well with low speed, but they didn't have the low speed control, and they did not have the control authority in transition from hover and VTOL to cruise and then back again. That's the part that's actually hardest. Making it fly like an airplane and making it hover like a vertical flight aircraft are actually far easier than getting through transition and conversion. So keep that in mind, and we'll talk a little bit more about control authority and balance of the airplane. Just a quick example of why I really love being a configurator. This is the Comanche. I was fortunate in the early 80s to be on the configuration team. And we were working on how to get the exhaust not to provide an infrared signature that would allow it to be threatened by shoulder-fired infrared missiles. And I'm at the knee of a great configurator, Bill Harper, and he says, "Hey, how about if we exhaust it in a long, thin strip along the tail boom, and it'll mix really well, and we won't have a plume." And Bob Frawley from Sikorsky, the propulsion lead, says, "Can we do that?" And Bill's comment was, "Yeah, I could do anything I want. That's why I love this job." I remember that like it was yesterday. The challenge is, it's not just about what you want to do. It's about finding a technically feasible solution that meets the objective. So it's not just cartooning. It is, in fact, innovating and trying to find a way to meet challenging requirements in a new way. So what are the constraints here? Of course, there's physics. There's perspectives and paradigms that's never been done before. And then there's resources, the funds, the material availability, the tools you have to get the job done, the team of people, and usually most important is time. Because if we had the luxury of time, we could redo it and we could iterate. So time is one of our greatest pressures. And just a little cartoon, we've got resources, we've got the paradigm. Sometimes we can afford things that other people don't get and they're uncomfortable with. And then there's physics. And there's our design. The conventional design is inside the paradigm and inside the resources and inside the physics. And then we have the unaffordable, and then we have the impossible. And our challenge is to move from the conventional, the dominant configuration, and be creative, but work within our constraints to try and achieve something novel that perhaps people aren't comfortable with, because the paradigms are a challenge, especially among your sponsors and the regulators and all those people who do in fact have to buy in. But that's the challenge of selling your story and making the case for the fact that it can be done and that it better solves the problem in the face of the risks. So a cartoon here, we've got a lot of ideas, and our challenge here is to think critically to try and understand which ones we're going to spend our time on, and more importantly, how much time we're willing to spend on an innovative idea, either to make it work or to recognize that it's not going to get there and we have to move somewhere else. That's perhaps the biggest challenge, something you're really excited about, but it's not getting there. That's why conversations with others and communicating in teams and diverse teams are so valuable, because we as individuals get really excited about our ideas, and we have to think very critically. And the goal is to filter out the ideas that are just not getting there and end up with a very narrow set. So as you're designing, you may have a whole bunch of creative things, but if you don't have the time to make sure they work, or they don't actually add value based on the amount of costs, how much work they are, you may have to abandon some of your good ideas. And that's the most strategic part of configuration design, is deciding what not to work on, what not to change, what is good enough. And I'll come back to that. So here it is. Here's the picture of the aircraft. Everybody loves the picture of the aircraft. I've been on programs where we don't really know what the requirements are, and everybody is screaming for a picture of what the aircraft looks like. And the challenge is, as soon as you do that, you lock yourself in terms of some paradigms. So the later you can put down the solution, the better. As a matter of fact, Gwen has been very clear in this GoFly activity that we shall not have an icon of an aircraft. We shall not be showing anything that implies an approach to a solution, because that immediately, whether you know it or not, it immediately narrows the design space. We really want the real resources, not the paradigms, but the tools and the team and the funds and the schedule and the physics to limit us. And we don't want to be stuck with paradigms. Now, oh, it's easy. Let's just put some parts together. That's great. Look, I've got these 4 parts. I got my rotor, I got anti-torque, I got a little bit of structure. Not so simple. First of all, those parts are only a very small subset of that OML, of that loft line. There's a whole bunch of other things you have to worry about. And so it's not only the rotor and the propulsion, the thrusters, but it's all these other pieces. Some of them have to worry about it, some of them don't. I don't think we have a requirement for communications, but it's not a bad idea to have communications. It's a whole bunch of other pieces. But even when you have that OML, the OML is not actually where you start. The OML has to fit everything on the inside, and that's the real challenge. It's invisible. People want to see the aircraft design, but the real challenge is trying to get in and understand all the piece parts and making sure it fits. So we've got this stuff on the inside, and that's actually the more interesting and the harder part, because that's where we have to make sure it fits together and it works together. We have to do both the form and the fit, and then we have to understand the functionality. Because in the end, if the functionality is not compliant with what it needs to do, doesn't matter what the system looks like, it doesn't succeed. And if the functionality is far better than what's needed, you may be wasting some of those valuable resources. So that's the challenge, is to balance that every piece just meets its requirements, and you spend your time and your effort ensuring that every piece is good. So, is there enough space inside your aircraft for all the things you need to fit? Have you thought of all the things that need to fit? You never want to hear an "oh shoot, I forgot," an OSIF, because that means rework, and rework is your enemy in terms of time and resources. So you really want to go slowly enough to make sure that every step is done with enough confidence so that you can get there at the end and avoid rework. But that's a challenge, getting there quickly. But if we go too quickly, we have to do things over again. So most important, do I have room for the payload? That's why I'm doing this. The aircraft itself is serving a function. Do I have the propulsion? Do I have the fuel, the stored energy? Unless I'm harvesting energy, I've got to carry it with me for the mission. I've got to have enough until I get either to the end of the mission or the point at which I can refuel. Structure, landing gear, pilotage, whether that's a person or that's the computing and the communication that allows you to do it remotely. And then I have, depending on the complexity, the utility and secondary systems, and more, but have I thought of all the pieces so it all fits? Does it all fit inside the aircraft? And does it, in all conditions, landing gear doors open on the Comanche, rotor blades spin, do the things hit each other? They move the way I intend, and then they also flex. So do I have clearances so they don't have interference? Very, very quickly, you'll find things will not continue to move past each other if you have negative clearance. So probably the most important descriptor of attributes at the front end is SWAP. It is industry worldwide standards, space, weight, and power. But unfortunately, it oversimplifies a little bit, because when I talk about resources, we also have to worry about space, weight, power, cooling, and cost. Let me talk first about space. So space, this is back to the form and fit. We're using nowadays computer design tools. They're incredibly powerful. They're a little bit limiting in terms of creativity, but they're incredibly powerful in terms of making sure things fit, understanding their envelope, overlaps, and interferences. So Comanche, I'm coming back to one of my a proud design. I was fortunate to be leader of a very capable team in terms of configuration. And this was a challenge. If you look at the shape, there were requirements on the aircraft in terms of different susceptibility bands. We had huge thermal challenges with a composite airplane that keeps all the heat in. So we moved to composites to save weight and allow us to come up with more complex shapes over metals, but that had its own challenges in terms of thermal management. Fitting everything in here was extraordinarily challenging. And if you look at this, in some ways it's elegant, and in other ways it's very confusing. In the end, it was the balance of all the things we needed to achieve. Did it all fit? Now, that word balance is pretty critical. We're an aircraft. We're being lifted by something, either a fixed wing or rotary wing or a deflected thrust, and it needs to balance. It needs to be stable. So we have to do a very good job of managing where that center of gravity is. So that's a huge piece of configuration design. You can't just stick things anywhere you want. This is a Comanche cartoon. You can see the left side of the aircraft with the station lines, the reference, the zero station is way out in front. The rotor was the center of lift when we're hovering. And on the right side, it's an illustration of our envelope, where the center of gravity is. Center of gravity had to be far enough away, low enough, and underneath it so that we had enough control authority so that we could hover. And when hovering, we had enough roll and pitch control authority to control the airplane and move around. So that's the challenge. Does it balance? Have you accounted for the weight and location of every piece? It's really an accounting function of just simply saying, how heavy is it and how far is it from my reference point, and building up that center of gravity. And you can see in the black here on the right side, it's not just the center of gravity, it's the family as you change the configuration, the empty weight, as you add the crew, the pilot, as you add any fuel, different configurations, as you move payload on and off. Not only is it static is it the static condition, but it's all the conditions with expendables. We worry about that with weapons, you worry about that with fuel, you worry about it with picking up and dropping off payload. And is it controllable? So is there enough authority in the system to overcome, to generate the moments that allow you to control this aircraft? And as I said, to remind you, the biggest challenge in the entire Vstall wheel was aircraft that did not have enough low-speed control authority. So please keep that in mind. And as you develop this system, convince yourselves that there's enough control authority throughout the envelope for this aircraft, and then you'll be able to convince others. And if you see the bottom bullet on the bottom left, safety includes limits on weight and CG. You can't just willy-nilly add something to the nose of the aircraft and be confident that it's going to work. Sometimes if you've been on a small turbojet airplane, they ask people to move from the front row to the back because they have to get that center of gravity in the right place before they take off so that throughout the flight, they have a safe envelope. Now, so we move from the space piece, which is form and fit, and now we move from form and fit over to function. This is where the analysis comes in. This is where I say, how does that design perform against loads, against aerodynamics, and does it comply? In other words, are we done yet? And the key is compliance. In the end, it comes down to the requirements, understanding your requirements, making sure you're not working to any assumed requirements that aren't real, which makes your job harder, and not forgetting any requirements, which makes rework. We talk about requirements creep and requirements churn, and that's because we don't have the requirements well understood, and it causes rework. So that's among the most valuable things you could do up front, is to say what you are going to achieve and being very clear about the assumptions about what you're not going to achieve. Now, we've got these amazing analysis tools available these days. It's really phenomenal how much computing we can do and how fast. And I'm confident many of you are looking at these tools and using these tools, but be very careful not to use the tool because you can. You should use the tool because you need to. So that's the paradigm at the top. When all you have is a hammer, everything looks like a nail. Please don't just use the tools for the sake of using the tools. Pretty pictures have no value. The goal here is to check compliance against the requirements. Here's an example of an aerodynamic analysis of a lobster because it could be done. Please don't use your time doing that because it might be fun, but in terms of meeting your objective, it's not going to help you. Use the tools where they bring value. And on that note, precision is not accuracy. You only need to be precise as much as adds value. You're looking for accuracy. You're looking for a means to generating function assessments. You're assessing function, strength, aerodynamics, and so on, to the level that is necessary to make the next decision. Just because the computer told you there were 10 significant digits doesn't mean you have that much knowledge. You probably only know things to a few significant digits, and anything that gets you more than that may not be a use of your time. I don't know if you've heard the expression, better is the enemy of good enough. But in fact, there's no such thing as better once you're good enough, because good enough means you're compliant. There is no such thing as better. Once you're good enough, you need to stop. And all that value, all those resources you're spending to make it better are robbing you of the ability to comply somewhere else. So better not only is the enemy of good enough, better can exist once you have good enough. Little cartoon of quite a long time ago. I had a lot less gray hair then. We were in a program where we really didn't understand a configuration. And so we had the Toyota test vehicle. I think it was a 1982 Corona. There were three of us, the driver who was controlling the speed, Roger Lacey here on the left, who was measuring the stability of the design, and I was in the front seat. That's a piece of aluminum siding and a bicycle spoke, and you can't see the model because this old Polaroid picture is all washed out. But we held it out the window and we kept trimming the tail until the damping of the tail went from overdamped to critically damped to underdamped. And it was probably took us about an hour and a half, not including building the model. And the data tracked incredibly well, and it was valuable to one of our proposals. It was great data. It was good enough. No calculations. Well, excuse me, a little bit of backer calculation to understand where we should start. We oversized the tail. We used aluminum from aluminum siding and a pair of tin snips, and we snipped the tail down until it got us there. That was sufficient precision to get us to a conceptual design that we're very confident, because the data tracked very well with the theory. So that's the point. You don't always need the CFD analysis of the cow. Sometimes a phenomenology, a measure of phenomenology is good enough. Enough information to make the decision so you can move on to the next decision. Now, probably the most powerful tool is the trade study. Down the left side, I've got the criteria, I've got the units, and we've got some kind of a target for getting dinner tonight. And our choices are pizza, chili, Chateaubriand, or sushi. And fundamentally, I only need an estimate to get me in the ballpark. And when you find that a feature is the same between all of them, it won't help you make the decision. You spend all your time on the features that are important. You spend your time and your precision and your resources only getting an answer when it's significant and driving the decision. So again, the amount of time you spend on this functionality assessment is a slave to the decisions that need to be made to decide whether it's good enough or it has to change. And another one of my great mentors, Dave Harding, said to me, the answer is not usually one of the trade study alternatives. So you do this trade study with a series of choices, and you find that each of them have a fatal flaw or a significant flaw, and the answer pops into your head. You don't need to go back and redo the trade. The trade was incredibly valuable in that it led you to the answer. It gave you all the learning, you understand the functionality analyses, you understand the trade space. So sometimes the trade study itself is just a means to coming up with the design, the one that's compliant, the one that's perhaps most elegant. So the trade study is a tool, but don't be a slave to it. If you get partway through and the answer is obvious, move on. Just a few words about risk. This is often discussed. It's nicknamed the Rubik's Cube. You identify the risks for anything that can go wrong, and Fernando Donas talked about this with his safety master lecture. You identify hazards. What can go wrong? What are the things that could be significant in terms of not complying and not being a successful system at the end? And you end up assessing them in terms of the likelihood of their happening and their consequence. And you spend your time worrying about the things at the upper right, the things that have a high consequence and they have a high likelihood, because if they have a very small consequence, you don't worry. And if they have a very low likelihood, you think about it, but you don't spend a lot of time on it because there's usually higher risks. What can go wrong? Now, I define risk as uncertainty, and I'll explain that in a second. It's uncertainty. And if it's things can go badly, you're not certain and they can go badly, that's a downside risk. And if things could go better, I'll explain in a minute. If things can go better, I consider that an upside risk, and most people call that opportunity. So we've got downside risks and opportunity, what can go wrong, and not being able to achieve it. If physics is your limitation, you need to understand that, because if it truly is a limitation, you need to move on, because it will not succumb to persistent effort, no matter how much you like your idea. So if we take this consequence, how do we deal with something that's high risk? Well, one way to do it from B to B prime is to do some analysis, to do some testing, to go out and do a Toyota test vehicle and see if the uncertainty can be diminished. Can I learn something that takes the uncertainty out? Analysis or test, or maybe designing it in a way where I have much more confidence about how it will perform. And that's where very simple tests can reduce your uncertainty. So the likelihood goes down, doesn't change the consequence. Alternatively, I can go from B to B double prime, and I can do something that reduces the consequence. One of those might be to design it, to have an alternate, to have a backup, to have some insurance, spend some time on something that's not quite as good, but if my primary design is high risk and doesn't work, that I can have a backup. It takes time. It's insurance, because it's of no value if B works fine. But if B fails, I've got B prime in the back. The other thing I can do is be conservative. I can reduce the consequence by being less optimistic and assuming less performance, simply adding margin, because margin is your friend. So if I get more conservative, the uncertainty is the same, but now my baseline is less optimistic, and some of that uncertainty becomes upside risk. So I turn uncertainty into opportunity by being less optimistic. So it's still uncertainty, but it's uncertainty that can help me. So this cartoon is a little bit of a tweak. So on the right side, I still have the risk cartoon, but I've changed the green to gray here, and I've moved the green over to the left. So I still have the same likelihood scale on the vertical, but now I've got consequence on the right and negative consequence is opportunity. So on my design A, I don't do anything other than change my expected performance. I add conservatism and promise less, and I reduce the expectations. Now, the consequence, not only is the consequence smaller of it not working as I planned, but now I've turned some of that uncertainty into opportunity. So again, margin is my friend, and I can have less risk. And the problem with risk, when it pans out, is I have rework because I'm not achieving my objectives. So conservatism, putting a little margin in, it might be space margin when you fit everything together. It might be weight margin by putting a weight contingency in. It could be schedule margin by putting a 1 week delay between finishing step A and starting step B. It might be budget margin called management reserve, where you pull a little bit of your budget off and make sure you've got something for a rainy day. So margin management is the job of the chief engineer and the configurator to make sure at the system level that you're managing the consequences of that uncertainty. This is a chart. It's not everything, but it gives you a little bit of an indication of all the little things a configurator has to worry about. Space, weight, power, clearance, balance, dynamic situations, all the different configurations. And you can see I put transition in terms of control authority. I put transition in red because that's usually the most insidious challenge that pops up late and therefore ends many of those Vstall wheel development programs. This is the job here, is the chain is, the strength is dominated by the weakest link, and you're trying to address them all and understand the weakest link and make it stronger. And again, don't spend too much time making any link perfect, because it's only as good as the weakest link in the chain, and the configurator needs to be looking at the entire system as a package and thinking very critically about the gaps, what's missing, what's been forgotten. The stuff that people are working on is the easy part. The stuff that nobody knows what's forgotten is the challenge. And my last chart, I just want to return to the goal here. Keep in mind what you're trying to achieve. That answers every single question. Does this help us develop a system that can achieve this objective? Does it move us toward it or not? And if it's not moving us toward it, it's wasting those critical resources of time and budget and team. I hope that was interesting. I hope it was clear, and I'm glad to answer any questions.
Great, thanks, Dan. A couple questions in already. First one being, how do you think drone technology can help the VTOL concept?
Okay, so drone is a buzzword everyone's become comfortable with. So if we're talking unmanned systems, uninhabited systems, or systems that can operate without a pilot on board. And the easiest of those is to simply take the pilot off board and be remotely piloted. And that reduces the threat to the flight crew, and it allows the aircraft to be much smaller, and it dramatically changes the onboard requirements. So you've moved the pilotage off board, or alternatively, you do it with autonomy. Those are all about that controlling the aircraft and knowing how to keep the wings level, keep the blue side up and the brown side down. And it's an opportunity, but fundamentally the aircraft, the physical system still has to have the control authority, the power, the energy, the durability to achieve the mission. So drone technology per se is partly getting the flight crew off the aircraft. If it's going to endure for 24 hours, it's better if it's uninhabited. If it's in harm's way, if it's, they call them dull, dirty, and dangerous. I don't know when and if we'll have fully autonomous aircraft with people on board until the regulators are comfortable with it. So I think, quote, drone technology can be valuable, but fundamentally this GoFly activity is about the air vehicle, the physical flying system, and it's not as focused on the pilotage and the means by which it's controlled. So it's interesting, but fundamentally it's not the thing that's going to enable it, because even if you decide to do your unmanned GoFly device to have it uninhabited, GoFly is requiring an equivalent of a person on board. So from a aircraft capability standpoint, it's still going to have the payload capability to carry an individual. I hope that answers the question.
Yeah, great. But to ask it maybe in just a little bit different of a way, you talked about manned versus unmanned. What about size considerations? Lots of the things considered drone-like are often really small in nature. Can you talk a little bit about the scale differences between those things and what we're talking about for GoFly?
Right. So again, the reason you would choose to be uninhabited and have an aircraft without a pilot on board, one is because of the threat or the boredom associated with long missions or dangerous missions, and the other is you can have a much, much smaller aircraft. So there's huge opportunity, and that's one of the and there's other opportunities like from a maneuver standpoint, the aircraft could fly as easily inverted as right side up. It could achieve much higher levels of G loading. To the extent that the regulators will allow you, you can have a much higher risk for the aircraft, and you don't have to have the redundancies and pay the cost of fault tolerance as much. Now, none of that is true for GoFly from a size standpoint, because GoFly is still requiring you, if it's operated by someone off the aircraft or operated by software, there's still the requirement to carry the equivalent of a person. So unmanned aircraft technology is extraordinary. I've been fortunate to have a lot of programs in my career working different aspects of it, and unmanning or uninhabiting the aircraft provides huge options from a configuration standpoint. And you can see what's going on with many of these small aircraft out there in configurations. But from a GoFly standpoint, it's not going to be as useful.
Great. And then jumping into the weeds for this one, in your opinion, is taper or twist more important in rotor blade design? Okay,
so if you take a look at one of the fundamental references on the topic, either Stepanowski and Keyes or Guessau and Myers, there's some very good books. Ray Prouty has got a bunch of articles and compendiums and a great book on the topic. The ideal rotor has, because the center of a rotating wing has got zero speed, because speed is rotational speed times the distance from the center. At the root end, it's moving very, very slowly. So use a combination of angle of attack and chord. And then the tip, you diminish the ideal tip goes to a point and it goes to zero chord, but practical designs have less than an infinite chord at the root and they have a finite at the tip. And so it's a balance, and you use both. Now, conventional rotor blades today on helicopter rotors tend to be untapered until you get to the tip, because from a weight and balance standpoint in manufacturing, and then the interference of those blades trying to change angle of attack at the root end. So they are both valuable. You don't have to choose between them. You use a combination of those. From a manufacturing and a weight standpoint, helicopters today have limited the amount of taper until you get out to the tip. But twist doesn't cost you weight. It's just a manufacturing challenge. And then the issue associated with enough stiffness that it holds its twist under the loads that it will see, under the torque loads, the twist loads. So soft rotor blades tend to unwind. It's called the tennis racket effect. As you spin them up, they will tend to unwind due to Coriolis forces. So there's a stiffness required once you put twist in. But again, both chord and angle of attack, so both taper and twist, are designed so that you can try and get as much lift out of the root end that's moving very slowly as you do out of the outboard end. So the outboard 40% or so is considered the working session because it does the majority of the work. And a cutout in the root end where the blades are turning very slowly tends not to cost you very much. So you usually save weight by having a cutout of some size.
Great, thanks. And then throughout your talk, you mentioned being on teams quite a bit. As people are putting together perhaps maybe small teams at this stage of the Go Fly competition, could you talk a little bit about what your thoughts are on ideal team composition is?
Okay, that's good. Diversity is great. Diversity is a challenge. When there's no diversity, everyone agrees, but they usually don't get the right answer because they're only looking at all the stuff they're comfortable with. Diversity is great. Diversity of personality, diversity of background, diversity of education, and diversity of style. I tend to be a conceptual designer, so I'm going to think in big ideas, and there are people who are going to buckle down and focus and make it real, and there needs to be a balance. Team size, I think you heard on Dr. Lewis's master webcast that team size, there's a limit to how many people because it gets too large. I think fundamentally the key to a very good team is very few, 1 or 2 people responsible for the system, and then delegating authority to portions, individuals or portions of the team. You might have individuals responsible for an attribute like aerodynamics or structural strength or weights, or you might have individuals or groups associated to a specific subsystem like the propulsion system or the propeller and fan. The key to that kind of team delegation are the interfaces and identifying very clearly the interfaces between what those teams are doing, because an interface between 2 teams is a contract. And if a team finds that they can't keep their part of the bargain and late in the program they tell the other team that they have missed their interface, they've created rework very late in the program for another team. So those interfaces become your contract, and margin to make sure you can achieve your interfaces is absolutely critical in a complex system. So I hope that helps. You know, when you get up, you can, on Comanche, on Chinook, on Osprey, Boeing, very large teams, very distributed. But the way we make it work is we've got a series of people responsible for the system, and then we delegate responsibilities to individuals or small teams, and they work with an understanding on what their objectives are, and they've got their own mini set of requirements, their interfaces to other teams. And if you can meet your interfaces, sometimes a team will negotiate to change an interface, but it has to be a negotiation. Because if you surprise one of your teammates at an interface with something that is different, you've created a problem for them and for the system.
Great, thanks. And then a couple of the previous masters have mentioned noise as perhaps one of the biggest challenges in this competition. What are your thoughts on noise and handling that requirement in GoFly?
It has almost never been a requirement per se. I'm sorry, civil aircraft have got specifications they've got to meet, and military have an objective. But the Comanche was the first military rotorcraft that had a specific hard acoustic requirement. It drove it to 5 blades. It was part of it having a fenestron tail. The MD-500, the MD-520N variation of the MD-500 helicopter had a no-tar tail for noise. But typically noise has been more of a fallout. This is a very exciting opportunity where noise has to be assessed up front. It drives you to things that are less efficient. It drives you to lower tip speeds. It drives you to larger diameters for lower loading of your thrust devices. It drives you to structure downstream of your propulsors that are more symmetrical so that you don't have the intermittent noise, so the frequencies associated with intermittent noise. So you may end up with radial struts where it'd be more efficient to have a strut straight across that fan. So noise is a very interesting master here in terms of a requirement, and it does find its way into each of the subsystems, because source noise, once the source noise gets out, you have no control over it. You've got to control the source noise, and usually the means to doing that make the aircraft less efficient. So I think it's really exciting that it's one of the fundamental requirements. And I'm really excited to hear these things, or not hear them.
So as a VTOL guy, do you have any thoughts on wings?
Well, yeah, I mean, a fixed wing is an incredibly efficient way to generate lift. It's better L over D, it's simple. Rotary wing thrust is the triumph of mechanics over aerodynamics. But the challenge with wings is they're heavy and they're only effective when you've got airflow, so they're only effective at speed. So they'll be valuable at speed, but when your speed, just like tails, when your speed is low enough, they're not effective. So they're just in the way and expensive and heavy. So you really need to take a look at trading against a very low effective L over D rotary wing system, whether it's edgewise or tilted, against a very efficient piece of structure that's dead weight at low speed. So again, it's control authority and it's balance. And when you put things underneath propulsors and behind propulsors, you get download. So it's not just the weight of these systems, it's where you put them. And if you want to move the rotors out, you've added structure. So there's a whole series of trades on how you think these things put together. And again, I'm interested to see what the teams come up with in terms of whether they're going to do fixed propulsors, multi-propulsors, tilting propulsors, wings, and so on. Our 20-minute endurance, it's not the same as range. It's an endurance requirement, but there will be cases where a wing will buy its way onto the system. But it has to buy its way on.
Great, thanks. And then before we close, I just wanted to make one clarification. You talked earlier about the flexibility in design and how GoFly hasn't presented any sort of picture of what things might look like. And just wanted to remind the teams that there isn't particularly a requirement for being able to wear the device. You can get in it, stand on it, sit on it, whatever your design is as long as it meets the GoFly criteria is the right design.
Thank you. Thanks for that clarification.
No problem. And then as we close here, Dan, do you have any quick words of advice for people competing in GoFly? What's your 1 or 2 sentence condensed advice for them?
Focus on the questions at hand and keep in mind the objective and whether what you do, each step of what you're doing is confirming that your uncertainty is manageable and it's good enough, and find that weakest link in the chain. Consider all the requirements and have fun. This is great.
Great. Thanks so much, Dan. On behalf of the GoFly team, we're really excited you were able to join us here today, and I'm sure that those listening and those viewing later will gain a lot of knowledge from your talk. So thank you very much for joining us today.
I hope you enjoyed it.
Awesome.
Thanks.
Great. Have a great day, everyone.